Okay, hello everyone. My name is Stefano Damiano and I'm presenting a road acoustics simulator called PYROADACOUSTICS that I developed together with Professor Toon van Waterschoot. And this is a quick outline on the presentation. I will start with the problem definition and a bit of context, and then I will discuss the features and architecture of the proposed software, and then I will conclude, if possible, with some audio demos. That would be nice, since it's a simulation. Why do we need this software? In the recent years, we have seen a lot of development of autonomous driving vehicles by the automotive industries, and the cars have been equipped with a lot of sensors that enable them to perceive the surroundings. And most of the research has been focusing on visual scene analysis with exploiting sensors like lidars and cameras. But we, as human drivers, do not only use our eyes to perceive the environment, but also exploit our ears to detect some useful acoustic events happening on a road. Think, for example, of a car that is honking that could imply some danger around, or some emergency vehicle with the siren active, or in general some events that happen in blind spots, but that we can perceive thanks to the sound they emit. This is why currently many companies are equipping cars with microphone arrays to process also audio events to enhance the safety and the perceptual awareness of the car. In order to develop such algorithms, we need large data sets, especially when it comes to deep learning approaches that are considered a sort of state of the art. And we have two mostly targeted scenarios that are the highway driving, in which a car is driving in an open field, usually at high speed, or the urban environment in which the car can be parked or moving at lower speed usually. And there is a lot of acoustic reflections due to building. Now, it is always difficult to collect data, and this is why there are few data sets available, and most of the actual research is using simulators. However, most of the existing tools target indoor simulations or noise control applications, and therefore can hardly be used to generate such specific data sets. For this reason, we decided to develop our own tool that we then deployed in a Python package. Now, the highway environment scenario is the scenario that we are targeting in this specific work and has some particular characteristics. So first, there is always a relative motion between sources and microphones, and due to the high speed, the Doppler effect has an important impact on the simulated signal. Then usually we have one main reflection or one only reflection that comes from the ground, and the atmospheric absorption is also important due to the large distances traveled by the sound waves. Now, to model and simulate acoustic propagations in the literature, there is a large use of delay lines that are simple DSP blocks that take a signal and delay that signal by a certain number of samples m. And if m changes over time, they are called variable length delay lines and can be implemented using circular array buffers. In this case, we have array pointers that writes the input signal sample by sample into the delay line, and its position is incremented by 1 at each simulation instant. And then we have one or more read pointers that are used to read the signal out of the delay line. If the distance between these pointers is governed by the sound propagation laws, then we get a simulation of sound propagation. In this case, the delay m can have fractional values, and in order to deal with that, there are fractional delay lines that are just normal delay lines followed by an interpolation filter. This is widely used to simulate acoustic propagation and Doppler effect, and we started from that and decided to include also the simulation of the reflection and of the air absorption that I have discussed in the previous slide. So this represents basically the architecture that we are trying to simulate. We have a single omnidirectional moving sound source and an array of microphones that are static and omnidirectional, and we want to simulate both the direct path and the reflected path with the ground surface as the only reflecting surface. This is the architecture that we have implemented. It's modular. You can choose to have different signal paths, but basically we have two delay lines that implement the acoustic propagation. And then we have some filters that are 3 gain elements that basically implement the attenuation due to the spherical propagation of sound, 3 air absorption filters that are FIR that implement the air absorption along the 3 different paths that you can see there, and 1 reflection filter that implements the properties of the asphalt surface. I will now get into more details about all these components. So as I said, the first issue is that we need to deal with the fractional delays, and we decided to implement 3 different interpolation filters in the simulator that are linear, all-pass, and sync interpolators that are commonly used in the literature. Now, these 3 filters have a different performance and a different complexity. And in order to show the trade-off, I have set up a simple experiment in which I have a single source that is moving along a straight line at constant speed and is emitting a sinusoid at 3 kHz. Here you can see the FFT of the simulated signal, and the linear interpolator is the simplest architecture, but also has some artifacts that you can clearly see. Yeah, you can see the pointer. These artifacts are much reduced by the all-pass interpolator, but there is still something that I don't know if you can see, and they are completely cancelled when we use the sync interpolator. However, with a higher complexity, there comes also a higher computational time, and in this table I am showing the simulation along different signal paths and using the 3 different signal interpolation filters. So this is the time in seconds needed to simulate 1 second of audio. So you can see that the sync is the more accurate, but also the more computational demanding technique. Then the first filter is the air absorption filter, and in order to model that, we started from the sound propagation law that allows us to compute the pressure at a generic position R, starting from the emitted pressure, and given the distance between the source and the microphone and the air absorption coefficients alpha, that are usually given in a dB scale in the ISO standard where they are defined, and they depend on frequency, and also on atmospheric parameters, in particular temperature, pressure, and relative humidity. We have a closed form expression for these coefficients that allows us, together with the sound attenuation law, to compute the amplitude response of a filter, given these attenuation at different frequencies, and this filter can implement the attenuation in a desired frequency range, as is depicted here. Now, from this, we can use some technique, for example, the weighted least squares method, in order to retrieve the impulse response of the filter. This is implemented by that function in Python. But the problem with that is that the procedure is really expensive, since the source is moving, so the filter must be updated at every simulation instant. And if you remember, we have 3 paths, so we have 3 filters that needs to be updated. Thus, to improve the speed, we performed a custom implementation of the weighted least square method. So we start from a given set of frequencies at which we know the desired amplitude response, and we want to design an impulse response of a filter of L taps. So in this method, we start from the generic definition of the amplitude response, H, big H, given the impulse response, small h. And if we impose even symmetry in this impulse response, we can obtain a zero-phase filter that can be later shifted to the right to make it causal, obtaining thus a linear phase filter. This can be expressed by this matrix formulation, and we need to find the small h vector that we can find by solving this well-known optimization problem that has a least squares solution. Now, what we noticed is that the matrix A that is depicted there depends just on the frequency omega and on the number of taps L. Thus, it does not depend on the distance between the source and the microphone, and thus it can be computed just once at the beginning of the simulation. And then, at each simulation instant, we can just compute the product between the pseudo-inverse that is pre-computed and the H vector, the big H vector, so on the left-hand side of the equation. Then the last filter that we implemented is the asphalt reflection filter. In order to do that, we started from studying the absorption properties of asphalt surface that have been widely studied in the literature. And we get some tables where we can find asphalt absorption coefficients that define how sound is absorbed at different frequencies. These are computed using impedance tubes and depend on the material, so each row of that table is a different asphalt mixture and has different absorption properties, and also depend on the incidence angle, and in the tables we find the normal incidence absorption coefficients. Now, as you may notice, we have the absorption coefficients up to around 2 kHz, and in order to enable simulate of a wideband signal, we performed a logarithmic extrapolation. So on this left-hand plot, you can see the coefficients of the table that are plotted with their average as a thick black line. And on the right, we have the extrapolated coefficients. We are interested, of course, in the reflection, not in the absorption, and I will get to that now. So we can compute also some reflection coefficients according to this formula. And they depend on the impedance of the asphalt surface, that is Z, on the characteristic impedance of air, Z0, and on the angle of incidence of the sound wave, theta. Now, these coefficients are related to the absorption coefficients by this formula, again, when they are computed at normal incidence. Now, if we assume a locally reactive surface, we basically assume that the impedance Z does not depend on the incidence angle. Therefore, it becomes a constant in the first equation of this slide. And therefore, we can compute R at a set of frequencies. And from these coefficients, we can then design a filter. We can get the amplitude response of an FIR filter and and retrieve the impulse response using the same method. Now I would really like to conclude with some demos, because that's a lot of words, but it's effective to make you listen to some sound. But I don't know if I am able to do that. Do we have some jack cable, maybe? Is maybe this one?
Yes.
Can I try? Yeah, it's here. Yes. I will use this for sound output. Let me try again. No, it's coming from here. Maybe this one. Okay, I got it. Yeah. It was coming from there. Okay, so sorry for the inconvenience. I will build up the complexities with these demos. So I will start with a simple scenario in which I have just a source that is moving along a straight trajectory and emitting a sinusoidal signal, and only the direct sound is simulated. So this is basically Doppler effect. Now I will add also the reflection and the air absorption. You can hear some interference between the direct and the reflected component. This is known as comb filtering, as you probably know. And in order to look at this better, I simulated the same scenario, but with a white noise source. You can clearly see the interference patterns there, and you can also listen to the effect. Sounds like a plane that is taking off. Then I'm also going to show some more realistic demos in our road scenarios. I will consider one source of interest, so first a siren and then a car honking, two moving noise sources that are vehicles, and three static noise sources that are basically ambient sounds. All the samples have been collected on online free repositories and simulated via this software. Since we can simulate just one source at a time, I repeated the simulations multiple times to build up the complexity with a set of fixed simulation parameters. And I have set random trajectories and velocities that you can see here. So the first example is a siren sound, and it sounds like this. It's also stereo, maybe you could hear something moving. And the second one is a horn sound. Okay, so this is to give an idea of what you can get. To conclude, this work has been published, both deployed as a Python package in the PyPy library, and also published as open source code on my GitHub profile. There's the link there, and also in the paper, if you're interested. And we plan to make some future extension by adding the wind noise on the microphone, and the directivity patterns of both the sources and microphone, and also some oralization in case we want to simulate a stereo signal. We also plan to conduct some perceptual tests to further validate the results that we obtain. So thanks a lot. This project is part of a European project called iSpot under that grant agreement. And if you have any questions, I'm happy to answer. Thanks.
This one.
Hello. My question is, do you plan in the future to introduce more complexity in the reflection, like if you're in a very snowy environment, or if there are a lot of trees, or if you're in the mountain and stuff like that?
Thanks for the question. Well, that's for sure possible due to the fact that basically the architecture and also the way in which the simulator is implemented is very open to extension. We don't plan actually to include vegetation or other reflections since we are dealing with since this is what we actually were targeting for the scenario that we needed to simulate. But for sure it is possible to include the presence of snow or of a wet road by just computing the properties, how the properties of the asphalt material change when the road is affected by this phenomena. So it is for sure possible, also in the current version, to do that kind of.
Is there a person over there? Hi, great presentation. Thank you for doing it. Doesn't it make sense, or do you have in the toolbox now the ability to include like the hard barrier in the middle of the motorway?
No, we don't. That would be something really interesting because it creates a particularly regular noise that could be really useful. But what we have seen in some literature is that there is the possibility to include that as a post-processing step. Since if you consider that the microphones are mounted on the car, and this is the scenario that we are actually targeting, the way in which you can perceive this sound doesn't change. It's the same thing that you listen when you drive with the window open, and you perceive always the same sound, that it varies just depending on the speed of the car. But it does not vary between the microphone themselves.
But you only include like the ground reflection, right? So aren't you fundamentally changing the geometry of the problem if you're only considering a single reflection, and that reflection's like, closer to the car window or wherever the microphones are, right? As opposed to down there where the road is.
That's very true. So it would for sure need an extension to do that. You couldn't include this with this direct scenario. But it is for sure possible.
But very cool. Thank you.
Thanks a lot.